Let's take a look at these. Can everybody see that? Why don't you just get where you can see that? I don't want to have to mess with making them bigger. A rectangular plot of farmland.
Bounded by side rivers. On three sides of the single strand of electronic fence.
Yeah, I'll read it. I'll read it. Rectangular plot of farmland will be bounded on one side by a river, on the other three sides by single strand electric fence with 2,200 meters of wire at your disposal. What is the largest area you can enclose, and what are its dimensions? Okay, so what do we do?
Draw a picture.
Yeah. Okay, so it's an optimization problem, right? Now let's go through our 5-step plan to optimize area here. First step, we need a picture maybe, right? And pictures do help. Picture, and we want to label the variables on it. So we've got here's our picture. We've got our river,
River's blue.
and there's our rectangular plot, okay?
An electric fence.
So we've got, let's just call these X and Y, right? It's rectangular. And we don't need the fence over the river. We just have the fence is only going to be on these three sides, right? It's just right there.
Yeah, but then one side of the thing is wide.
But it's got a river there, so they
Bounded by the river.
Well, if there's cows, what if they get there and drown?
I know.
What if there's
No, these are smart animals.
These are smart animals, aren't stupid.
What if they crush some gators?
Okay. So what's next step? We got our dimensions on there.
Find a parent equation. Yes,
Find the primary equation.
primary equation. That's what I meant.
So what is the thing we're trying to maximize or minimize here?
The area of the
Area. Maximize area. Okay, so we know that area equals what?
X times Y.
X times Y. Okay, so there's our primary equation. Now, if our primary equation is a function of only one variable, we can just skip all the way down and do the calculus stuff, right? But it's not. We got x's and y's in there, so we need an equation of constraint, a secondary equation. Now, what's our equation of constraint? What's the thing that constrains us here? Constrains our area.
Length of wire.
The perimeter. Yeah, right. The length of wire.
The
So
2200
we could call it a perimeter of sorts if we want to, and it's 2,200, right?
meters.
And what is it in terms of x and y?
2
2y
wide.
plus x. We don't need the riverside,
Yeah.
right? So 2y plus x equals
Did you calculate the table again?
2,200.
Meters.
So there's our secondary equation or equation of constraint. Now, which of the two variables do we want to solve for? In this case, it doesn't really matter too much.
Y.
X.
Probably x because
Why?
it's just easier, right? It's easier to get the x by itself. So if we isolate x, x is just 2,200 minus 2y. Let's put a box around that because we're coming back to it. Okay, that's our substitution equation. So if we do that then, if we take this x and plug it back in up there, what do we get? Area.
100 minus y.
Okay.
Times, no,
Yeah.
just kidding,
Good
just
job.
kidding.
That was a good one.
No, that's x
Wolves.
times
Wide.
times
Y.
y. Yeah. So if we distribute the y, what do we get?
Y minus
2200 Y
2y.
minus 2.
Okay, now I'm running out of room, so I'm just going to go to a page here.
All right. Oh no.
You told me you had room right there, though.
I was feeling cramped.
Why can't you make these bigger larger?
I can make these as big as I want, but I can't make the other one I was.
Make this big.
Why can't you just zoom in onto your things relatively small?
I normally could, but on the Math Excel stuff, I can't for some reason. I don't know. So what did we have here? We had area equals, what was it again? 2,200.
Minus 2y.
Right, 2200 Y minus 2Y squared. Yeah,
So if I distribute,
yeah.
okay?
So you zoom in, draw there, and then go back out. That's somewhere.
Okay, everybody good with that? So we got area as a function of the single variable y. That's good.
Yep.
So we're about ready to do calculus. But before we do the calculus, let's find the domain, because that can make our calculus job easier. We only need to find the maximum area on our domain for y. And mathematically, the domain could be anything, but we're limited because this is an actual problem about an area, right?
That's the hardest part.
That's gonna be fun.
So this is probably the hardest part, you're right. So if we go back and look at our picture here, what's the smallest that y could be?
0.
Yeah, I mean, we could let y shrink down to 0. Now, if we did that, that wouldn't make a lot of sense because our fence
All the animals.
would run all the way along the river and it would have no area.
Well, what kind of animals are they, and do you on the river?
Okay, they're three-dimensional animals, and so it wouldn't work for them.
They could be in the river.
Yeah, that's what I'm saying.
Then the problem
These
becomes...
animals don't swim.
What if they're alligators?
Fish do. Okay, anyway.
No,
So I actually have to make an important point here. The question, the value of 0 is a good one, but it's a lower limit, right? It's not going to, we know it's not our answer.
What if the river
But in our domain, no more what about?
It's gotta be greater than
What about?
zero.
What if the river fluctuates?
What if the river? Yeah. What if it fluctuates?
Oscillation of the water.
Or what if the river has a slight curve to it?
It's a straight river.
I don't understand. Is it
There's no such
man-made?
thing as a perfectly straight river.
No, it's perfect. This one is perfectly
There's
straight.
such thing as a straight river.
Okay, so now what about y?
Yeah.
We said the lower limit for x, or for y is, for y is 0. What's the upper limit? And where we want to go with that is
2200.
1,100.
here. Right? Now these two variables,
Remember
remember
1100.
remember this thing?
1100.
Well, we got these two variables like this that are contributing to a quantity. When one variable goes up, the other goes down,
Yeah.
vice versa, right? So by finding the maximum value of y, we are also simultaneously finding the minimum value for x, right? So now, what would the minimum value for x be? 0. So if x were 0, then look what we get here for y. We get the equation 2200 minus 2y is 0. So 2y is 2200. So y would be what?
1,100.
1100. Okay. Right?
Or someone would say that.
Now, did everybody get that? Look, I don't want to gloss over that. That's an important trick. When you're trying to find the domain, when you're finding the extreme values of the domain in a problem like this, remember that the maximum value of one quantity correlates to corresponds to the minimum value of the other quantity, right? And frequently, it's easier to think about it in terms of a minimum than a maximum. Okay? So minimum max, maximum y. All right, so we said 1100 was our upper limit. So there's our domain. That's the only part we have to consider the calculus for now. We'll just do the calculus. We want to maximize area, so we're going to take derivatives, right? What's a prime?
2200 minus 4y.
Minus 4y, good. Okay, now that would, it's never undefined. It would equal 0 at y equals what?
2200 divided by 4.
Yeah, 4y would have to equal 2200 for that to subtract to 0, right? So 2200 over 4 would be 550. Okay, so there's our one critical number, is at y equals 550. Now, while we're at it, we might as well calculate a second derivative because it's so easy. What is the second derivative?
Now, why would you do that then?
Well, you'll see.
-4.
Negative 4. Okay, so when we make our table then, the second derivative is always negative. So that's going to, by the second derivative test, that'll tell us immediately what kind of extremum we have here at this critical number, right?
Third derivative is 0.
So let's make our table. So let's go ahead and put in our domain. We said we went from 0 up to 1100. We had one critical number at 550. And that was a 0 for the first derivative, and the second derivative had a negative value there. So is it concave up or down? Happy or sad? It's sad, right? So it's a maximum. Okay? So that's what we're looking for. We found that y equals 550 is the answer, but we may need to fill in some more blanks there, right? So if we go back to the actual problem, it wants to know what is the maximum area. Well, we can fill these in hopefully in any order. We know that let's find the other dimension. If y is 550, what is x going to be? Yeah, it's going to be 2200 minus 2 times 550. So x, whoops. So x is 1100. Okay. So then we got 1100 by 550. So if we filled in those on our, this must be, let's see, x is this guy. So that's 1100, that's 550. Let's start putting the answers in. What's the length of the shorter side? 550. Longer side? And then the area? Well, we could either go back to here and plug it in if we want to. Plug it in right there. Right? I could put in for y, I could put in 550 and see what we get and do that quadratic equation. Or probably easier, we're dealing with a rectangle. So just 550 times 1100 is what? Some answer. What our calculator tells us. Right? Okay? Make sense?
I mean,
Okay?
go ahead.
Yeah.
Where'd you get the 550 from the first time? Who was it?
The 550. That's we found our primary equation in terms of a single variable. We differentiated that, and we set the derivative equal to 0 to find the critical number, right? When we solve that equation, 2200 minus 4y equals 0, our answer is y equals 550.
Okay.
Okay? Yeah.
Wait, so you know that's gonna work because it's the maximum in the second derivative.
We know that this is a maximum because the second derivative was negative there.
What if
If it was positive, it would have been a minimum, right? Because the concavity of the second derivative. If I know that I have a 0 value for the first derivative, right? I have a critical number where the first derivative is 0 at this value of independent variable, y in this case. Then I know that that's a horizontal tangent line, right? I just need to know, does the curve, if it's concave up, then that point of tangency has to be a minimum, right? That make sense?
Yeah.
If it's concave down, that point of tangency, that horizontal tangent line, must be a maximum. The sign of the second derivative tells us the concavity, right? Yeah.
Well, I thought we had to find the signs around it.
Well, no, that's you don't. That's the first derivative test. We have that option, but it's better. We always want to work as far down the table as is convenient to do, right? Instead of having to check 2 test points. What Yan Yan's saying is we could have checked a point like at 100 and checked a point up here like at 1,000 or something, and checked the signs of the first derivative if we wanted to, right? But that's more work. We'd have to evaluate 2 signs instead of just 1. Right? If the second derivative is convenient to calculate, to find, then it's always easier to use the second derivative test than the first derivative test. Everybody understand the difference between the two? If I had checked, I guarantee you tell me what would the signs have been without even, if we know that this is concave down, what would the sign of the first derivative have been to the left of 550? It would have been positive because the function would have had to have been increasing there. And if we had plugged it in, we would have gotten a positive sign back. Okay, so that would have been positive. What would it have been here? Negative. And we can see that if we want to by looking at the function. If I put in 100, I would have gotten 2200 minus 400. That's very positive. If I put in 1,000, I would have gotten 2200 minus 4,000, which is very negative, right? And so that would have told me, okay, it's increasing, and then it's horizontal tangent, and then it's decreasing. That also would have told me that this is a minimum. But why not? If you can just calculate a very, very simple second derivative like this, why not do that so you can just fill out, just look at test 1 point instead of 2. Yeah.
What I don't get is for the second derivative, we put a negative 5 and 50, but it's a negative for everything.
It's negative for everything, right?
Does that mean it's a maximum everywhere?
No, it means it's concave. It's concave up or down everywhere. But this happens to be the 1 point where we have a horizontal tangent also. So it's the maximum. But wouldn't you agree that if I know the function has a horizontal tangent and I know that it's concave down, what am I talking about right there? It has to be a maximum. It has to be a peak. If the tangent line is horizontal, so if I set a ball there, it's not going to roll, right? And yet it's concave down, then I'm talking about the unique point that's actually at the peak of the mountain. Right? If I were to sketch a quick graph of this, I think that'll answer your question. What if we did this? Right? I know that this thing is doing this, right? Well, I kind of got it off a little bit. We know that it's concave down everywhere, but we found the one place where there's a horizontal tangent line, so that's the peak. If I had found a tangent line down there, it wouldn't have been 0, so it wouldn't have been significant. That make sense? Okay. All right. So, on problem 2.
Where's the maximum area?
You gotta put it. 1100 times.
Well, we can figure that out. That's going to be
Whatever that is.
55,000 plus 5,500. So it's 61,500. 60,000. That's what I think. Okay, so how about this one? Suppose R of x equals 96 times the square root of x. That represents the revenue, and C of x equals 3x squared represents cost, with x measured in thousands of units. Is there a production level that maximizes profit, and if so, what is it? Okay, so how do we find profit if we're given revenue and cost? What's the simple formula? What is profit in terms of revenue and cost? Revenue is how much money we're bringing in. Cost is how much money we have to pay out.
How much you make?
Right. So what would that be then?
It's like
Revenue minus cost.
Yeah. Right. Revenue minus cost. Right. So let's write a profit function then. So profit as a function of x would be revenue, 96 times the square root of x minus c of x, 3x squared. Okay, now, what would our obvious domain be here? If x is the number of items we're producing in thousands of units, what's the smallest x could be?
1,000.
Well, no.
Well, 1,000.
I mean, it would be very smart, but it could be 0, couldn't it? Right? I mean, we could not make anything. We couldn't make a negative number of products, but we could make none. And then we can just make as many as we want to after that. There's no practical, or there's no limit on how much we could make, but probably at some point it's not going to be cost effective. Okay, so.
Non-negative.
Right. So that's our domain. Just some positive number of widgets that we're making. Okay, so how are we going to know then? We want to know, is there a production level that maximizes profit? If so, what is it? What do we do?
Find maximum.
Yeah, so this is a much easier problem than the first one. We don't have to draw any pictures or anything. We're already down to step 4. Actually, step 5. I mean, their step 4 is the domain. There's step 5.
There's only 5 steps and we're done.
We haven't finished step 5. We just begun step 5. So what do we do in step 5 with this?
Solve for x.
Well, we got to maximize that function. So how do I maximize a function?
Find your
Derivative. I got to find critical numbers. Okay, here's my function. I want to find the critical numbers and then evaluate and find out which of those is a maximum. Okay, on our domain. So p prime of x is what? Now that's easy. That's just 6x, the second term. But what about that first one? How do I deal with the square root of x?
turn it into a power.
times x to the 1/2.
X to the 1/2.
You
Okay.
get 1 1/2 of 96.
48 x to the negative.
So yeah, so what do we do? What's the derivative of 96x to the 1/2?
48 x to the negative x.
Bring the 1/2 down. Good. That makes it 48, and then I get x to the minus 1/2, which is the same thing. Well, I'll write it down. And then here I just get a minus 6x. Okay. And so if I want to find the critical numbers there, right?
Do we want to just take the second one?
I would say probably taking a
I'd
second
say it's
derivative
pretty
is
easy.
fine here. It's not a big deal to do. If we take the second derivative, and that's sort of optional, you wouldn't have to, but
No, we'll do
say
it.
we do. What do we get from this one? What's the derivative of 48x to the minus 1/2? So multiply the minus 1/2 times the 48. Good, I get a negative 24 x to the negative 3/2. Good. Minus 6. Okay. Now, that probably was worthwhile because what could you tell me if I plug any positive value of x in, what's the sign of the second derivative going to be?
Positive.
Oh, it's got to be negative, doesn't it? Because I've got a positive number to the negative 3/2. That's just 1 over x to the 3/2. That part's going to be positive, but times negative 24 makes it negative, right? Minus 6. Okay, so then everybody, I mean, that will be negative. We wouldn't have had to have done that. We could always use the first derivative test, but I'd say that's probably worth it. So now we got to solve this though. Here's our first derivative. In fact, I'm going to grab that and we'll go to the other page. Okay, so there's our first derivative, right? We want to find, and our domain, remember, was 0 to infinity, yeah. Okay. So we need to find, where are the critical numbers? The first derivative? Where it's, say it again, where it's, well, not where x equals 0, where the derivative equals 0, or where the derivative is undefined. So we got two things to think about. Let's write this, how about? Write this x to the minus 1/2 as a square root of x on the bottom, right? It's 1 over x to the 1/2. X to the 1/2 is just a square root of x. So there's our function. Now looking at that, where is there any place where that derivative function is undefined? Any value of x that would cause me to take a square root of a negative number, right, or divide by 0?
Denominator is negative.
Okay, so when the denominator is negative, but look at my domain. My domain doesn't include negative numbers anyway, so we're okay there. We dodged that bullet, right? But it can't be 0. X equals 0 would force me to divide by 0, so that's technically, we could say, is that a critical number? Well, it's an endpoint anyway, right? So we know that x equals 0 is someplace where technically there's a critical number, but we're going to check it anyway because when we're looking for a maximum value, we're going to analyze always.
We don't need to.
We don't really need to, do we? Because if we put 0 in, I mean, if we go, 0 is ridiculous. If we look at our original function, if I put 0 in, what do I get back for profit? 0. So that's probably not going to be the answer anyway, right?
Probably. Oh.
Yeah, it's not a very good company.
Well,
But
with this economy, it's probably going to be negative.
yeah, maybe. So let's look for the other one then. We got sort of a non-important critical number at 0, but there presumably might be another critical number that is important. So we'll find out by setting the first derivative equal to 0 and solve it. So now we got a little algebra to do. How do we solve this equation? There's a couple ways we could do it, and I think they're equally good. Well, we can't isolate x because there are two x's. Say it again. Okay, so one way we could get rid of the radical. We could isolate the radical and square both sides. That's one thing we could do. Okay. We could also, if I add 6x to this side, I get the equation 48 over the square root of x equals 6x. Okay, so yeah, what if I cross multiply here? If I cross multiply, and I wouldn't have to, I could isolate. You know, once again, as we said, going back to honors algebra 2, we did a bunch of this stuff. Remember, where we'd isolate the radical and then clear the square both sides, right, to solve.
Yeah.
We'd have to check the solutions though to see if there were an extraneous solution there, but we could. If we cross multiply, I'm going to get the square root of x times 6x. That's the same thing as x to the 1/2 times 6x. Now what is that? What is x to the 1/2 times x to the 1?
Negative 1/2, x negative 1/2.
One
Oh,
and
yeah.
a half.
If I cross multiply.
6x and 1.5. Yes.
1.5, 3/2, right. So when I multiply like basis, I add the exponents. So when I cross multiply, that's going to give me 6x
Bingo.
to the 3/2 equals 48 times 1, right?
Divided by 6.
Okay, good. We'll divide by 6. And we get, okay, if we divide by 6, we get x to the 3/2 equals 8. Right?
Yep.
We buy that?
Yep.
Okay, and then, so now how do I get the x by itself?
Can you exponentiate to the 2/3?
Okay, yeah, I can take both sides to the 2/3 power. Anytime I take both sides to a power, though, remember, that means I've got to check my solutions because they may be false, maybe extraneous. So if we do that, if I take both sides to the 2/3 power, I get x equals 8 to the 2/3, right? Everybody see that? And that makes sense, doesn't it? If I take both sides to the 2/3 power, x to the 2/3, x to the 3/2 to the 2/3. If I take a power to a power, what do I do to the exponents? I multiply, so they would cancel. Right. That's why we did that, right?
Ultimately, that's what I was doing.
Okay. So now so the answer is x equals 8 to the 2/3. That's an integer. How do we evaluate that if we take an 8 to a fractional power like that?
Divide by 3 and multiply by 2.
8 to the 2/3 is really just 8 to the 1/3 squared, right? Now what's 8 to the 1/3? What's it mean to be to a 1/3 power?
Divide by 3.
Cube root. Okay, so the cube root of 8 is 2 squared.
4.
Okay.
4.
Jefferson?
Okay, so there's our answer, right? Now let me ask you another practical question. Algebraically, the math gods would insist that we go back up and check that. They would insist that we go back up and check that in here to make sure that it works, because it could be an extraneous solution. But being as this is a small part of a bigger problem, and all we're really trying to do, remember, is
I don't care about small stuff.
we're trying to see what's the maximum value for profit. We only got one critical number, which may or may not work anyway, right? Are you following my logic?
Yeah.
Why don't we just plug it into the original function and see? There's no reason for us to go back
Too
and
much work.
see
Too much work.
if squaring both sides introduced an extraneous solution, because if it's extraneous,
Doesn't
when we
matter.
plug it in our table and check it, it's not going to show up as a maximum anyway.
So you're telling us to
Right?
ignore the math.
Yes, in this one isolated case, we ignore the math guys.
Blasphemy.
Okay, so
Or math.
Polygamy.
I don't think that applies.
I can't go back. I have to.
okay, so our one critical number was at x equals 4. If we make our table,
Plug it. Chug it. 24 is 0. That's true.
and we won't even bother with the second derivative. Pretend we didn't do that. So our domain went from 0 up to infinity, so 0 and up. We had one critical number at 4. That was a 0 of the first derivative, right?
Yeah.
And so we'll just use the first derivative test and see what's going on. The value of, let's try test
What was
points
the second
at,
derivative?
well, pretend we didn't take that.
Why?
I just pretend. We need a little practice with the first derivative test. So if I evaluate the sign of the first derivative at 1, what am I going to get? 48 divided by the square root of 1 minus 6 times 1 is positive or negative? Positive. What about at 10? 48 divided by 10 minus 60 is negative.
How do you know the first derivative is 0?
Because that's what we found when we solved, right? If we go back to that last page, right, we solved this equation. We knew that we were setting the first derivative equal to 0, so we added 6x to this side, and then we just cross multiplied.
I forgot we had
Okay. And so we know then, if we look at what this is doing, it's got to be maximum because it's increasing, horizontal, decreasing. So there's our maximum. Do we even need to check 0? If there's only one maximum on our domain, then it has to be the absolute maximum, right? And so there is a value of x that maximizes profit. It's x equals 4, and I think that was 4,000 units.
Yeah.
So we would plug in, here we would plug in 4,000, right?
Why is it 4,000?
Because x is measured in thousands of units. Tricky, isn't that tricky? That's me.
I don't get you.
Wrong. That's messed up.
Now, if you put in 4, of course I would have gone back and
Good.
Would you give us full credit?
9/10 credit.
but don't try it. Just do it right if you remember. Okay?
We want to make you work a little bit.
Yeah, I work hard enough. Don't do that. Okay, so how about this one? Find the dimensions of the open rectangular box of maximum volume that can be made from a sheet of cardboard 31 by 17. Now, we've done a bunch of these. Maybe we can sort of make this one a little quicker.
Nope.
How are you so sharp? So sharp.
Okay, we did one just like this. So if we're starting off with 31 by 17, remember this is the one where we fold up the corners, we cut out the corners and fold up the sides,
Yeah.
right? So
What would in that corner is going up the corner? What are you doing right now?
I'm cutting out the corners and folding up the sides to create
Cube? Not box. Cube.
to create an open box. Right? Okay, so if the whole thing is 31
That's some good geometry right there.
by 17, then what's the only variable here we would include in our drawing? Call it whatever you want, but x, sure. So x is the how far in we're cutting those squares, right? It's going to be the side length of one of the square cuts.
Yeah.
What does that correspond to on our folded up open face box?
Isn't it the top?
No?
The height.
Height. Yeah, that's x. Good. And then so now what's going to be the length of the base of this thing?
The longer.
31.
31. But when I fold the sides up to create the
31 minus 2x.
there you go, 31 minus 2x, and then what's going to be the width?
Yeah.
17 minus 32.
Okay, and so this ends up being, actually, once we get the picture drawn, this one isn't too bad because when we're trying to maximize volume, right, and that's only going to have x's in it. So the volume is just going to be what?
Multiply volume.
Yeah.
That times that times that.
Yeah. X is plus 9.
Okay, makes sense?
Yep.
Now, for our domain, what's the here's the one thing we got to probably look at. What's the smallest that x could be?
Can't be 0.
Well, I mean, 0 would be kind of the lower limit. It wouldn't be a practical value, but it's the lower limit, right? So our domain would be from 0 up to what?
We can't go to 9.
Okay, we can't go to, you're right. What's the biggest we could go to before
8.5.
8.5? Because as we make these cuts bigger, well, I can only make them so big because the original cardboard sheet's only 17 something across, 17 inches across. So the most they could be half of that 17 before the cuts run into each other, right? Okay, so then we end up with 0 to 8.5. Okay, there's our domain. It's pretty easy. We would just probably, now when we're doing the calculus, practical question, when we differentiate this, how do we want to deal with that derivative? In other words, do we want to deal with this as using product rule like this, or do we want to expand it out? There's a definite right answer on this as far as I'm concerned. Product rule is going to be hard. Yeah, it's going to be hard because think of all the extra steps we have to add to that. Even though it's a little bit of extra algebra to expand this out, it's not very much. Look, I'm just going to FOIL out those two. And then when I distribute an x, I'm just kicking up the powers of x by 1, right? So we'll take the little bit of extra time and do the algebra to set this thing up in order to make the calculus easy. So we would definitely expand this out and get a polynomial that's then extremely easy to differentiate twice. You get a first derivative and a second derivative that would both be really easy to do. Right? Here we would. No one, he really was offended by the second derivative. Now here we would definitely do it because it's a polynomial. Polynomials you would always just differentiate until cows come home. And they're easy. Every time you differentiate them, they get. Whoa.
Okay.
Oh! Look at the water. Okay, so that one, I'm just going to dispense with that one then. Right? That one wouldn't have been a big deal. We had the original function.
Dispense? We just wasted like 3 minutes on that.
Okay, how about this? We have time to at least talk about it. Yeah, these are good. These are good. We got to do one of these. We're not going to be able to finish it up, but let's at least get it started. We'll at least get it started.
I honestly don't think we can start.
What do you think?
We have 3 minutes.
Ask the rest of the class what you think.
Good point.
I don't want to get started then be like, oh, then forget it.
Okay, but I agree with Danielle. This is what we got to do. We got to tomorrow we'll finish
Battle
this
Royale
up.
question. I have a question.
What's that?
What you got? Question? Battle Royale.
Battle Royale. Battle Royale. Okay, my Battle Royale question is.